All right. So thank you for a chance to present this presentation in this great venue. And the title is indeed Macromolecular Genus as a Measure of Complexity. And the aim of our research and hopefully of my talk is somehow to convince you that one can take advantage of some topological invariants to understand and somehow quantify complexity in the sense I will explain in a moment of macromolecules. And saying macromolecules, I have in mind, of course, RNA, proteins, maybe also DNA. And in this conference, we already heard and will hear some talks about topological properties. We heard words such as knots and lassos. And I will talk about some other manifestation of topology, not so explicit. It is related to some two-dimensional surfaces and the property which is called genus, and this is not just a configuration of some molecular chains, as in case of knots, for example, but a kind of auxiliary set of tools which help us to quantify somehow that complexity I have in mind. So let me first explain what this genus is and how it has to do with this complexity, by saying complexity, I somehow mean the structure and interconnections between various bonds which we have in some polymer-like chain. In particular, this could be RNA chain, as we have it here, but it could be also protein chain and so on. And the idea is to relate this chain to these two-dimensional surfaces, as I mentioned, and one can do this in particular by using as an intermediate step some objects which are referred to as Feynman diagrams, in particular in physics. So what is nice in this activity is that it somehow connects various developments, well, on one hand from biology side, but also in physics and quite abstract mathematics. And in particular, we discussed this connection in the following paper, whose title is Topological Recursion for Chord Diagrams, RNA Complexes, and Cells in Moduli Spaces. So these chord diagrams are, you might say, related to physics. RNA is, of course, biology, and moduli spaces have to do with mathematics. And this was published in Nuclear Physics B journal, which is a physics journal. So this shows how it interconnects these disciplines. And as another kind of confirmation of interdisciplinary of this research is this conference, which took place 2 years ago in Strasbourg. It was a conference in the series of meetings of theoretical physicists. But when you look at the list of speakers, you find both biophysicists and also quite, let's say, abstract mathematicians, such as Bob Penner. He was, in fact, an organizer, or Jürgen Andersen, who was supposed to be here, but he finally, as far as I know, didn't come. So let me explain what this genus is, and first, what is a ribbon graph, which appears as in an intermediate step. Probably some of you are familiar with these ribbon graphs. They are often used to describe structure of base pairs in RNA, and this is a very simple object. So instead of looking at such a chain, we kind of stretch it so that this main chain is on the horizontal axis, and then all bonds which we had here are represented just by arcs which connect corresponding residues. And when we have such a chain, to get ribbon graph is again a very simple operation. We just take each ingredient in this picture, so this backbone chain or many backbone chains, there could be more than one, and each arc, and replace it by a ribbon like here. So it has some definite width. So this is a ribbon graph. This is characterized by three numbers. The number of backbones, this is 2 in this example. When we consider a single chain, this is just one backbone, but one could also consider complexes, then one would have more backbones. We have number of chords. By chords, I mean these arcs or just original bonds that we had. This is denoted by n. And also number of boundaries, and this is the crucial thing. The boundary is the boundary of this graph, but considered as a two-dimensional object. So to look for a boundary, we have to look at this black boundaries of those ribbons. We can go around and count how many of these boundaries there are. Maybe this is better seen in this example. So here we have one backbone, we have 2 chords, And the boundary is just this red thing. If you go around and look carefully, you will see that there is just one boundary. If you start from this point and go around, you will come to the same point. So there is one boundary, and there is the Euler relation, which tells you that if you have such a graph, you can draw it smoothly on some two-dimensional surface, which may look like this, which has some definite genus, or in other words, just the number of holes. So in this example, using this Euler relation and substituting these numbers, we can find that this genus is equal to 1, which means that this auxiliary surface is a torus, and then we can draw this object smoothly on this surface. And my aim is to convince you that this kind of abstract operation has some meaning in the realm of macromolecules. So at first I will present some results for RNA and then for proteins, which are main objects of this conference. And these results should appear hopefully this year in a paper which we wrote in particular with Joanna and also with Abby Anderson, Cody Gary, and Sebastian Zając. So what are RNAs? We all know they are just single-stranded polymers made of those bases, ACGU. You can discuss various base pairs which are formed, either canonical one, AUCG, or non-canonical, which will be also of interest to us. And there are various examples of those RNA strands. There are several hundred of them in PDB, which can be analyzed. One of most interesting, which will be also quite interesting to us, is ribosome. It consists of two subunits. One of them is so-called large subunit, which consists of like 3,000 nucleotides, and another one is small subunit, which consists of 1,500 nucleotides. So this is quite a big structure, and then the manifestation of this genus analysis will be most interesting in the case of ribosomes. But before I come to ribosome, let me add a few other comments. So first of all, this complexity I have in mind in the context of RNA, for example, has to do with the presence of pseudoknots. So in fact, if we have such a simple structure in RNA, then if you would try to see what the corresponding surface would be, if I want to draw this chord diagram I mentioned before, in this case it would look more or less like this. And in fact, one could use this Euler relation to see that genus of such a structure is 0. And in fact, this is always 0 if we have this chord diagram in which those chords do not intersect. So for each diagram of this side, we have genus 0, so this is not quite interesting. And this is also fine for us because we would like to consider this complexity of bonds, so we look for something more interesting. And when we have pseudoknots, so a structure like this is well, in a simpler way, this structure more or less is equivalent to something like this. So then these chords intersect, and this genus is non-zero. And it has some interesting properties which enable us to quantify somehow how complex those different pseudoknots are. Here is some more realistic structure taken from some particular RNA chain, and then this corresponding diagram. I should also add that the structure prediction with the presence of pseudoknots, as you must also know, is an NP-hard problem, so this is also one motivation for us to consider this, topic. So, in fact, RNA structure is more involved, as you well know. So, thus the structure of bonds I just presented is kind of simplified, but in fact, bases of RNAs can interact in various ways. And one way to describe these interactions is to divide them into Watson-Crick base pairs, which are responsible, for example, for forming double-stranded helices or certain secondary structures. And also non-Watson-Crick base pairs, which are responsible for forming various RNA motifs. And the classification of those base pair structures has been proposed, one of the classifications by Leontis in Westhoff, like 15 years ago. And what is important that you can look at those bases simplify them by triangles which have 3 edges, so-called Hookston edge, Watson-Crick edge, and then sugar edge. And instead of considering the full base, you consider just a triangle. So that's one issue. And then interactions between base pairs amount to matching 2 triangles together along 2 edges. I mean, you take one edge from one triangle, another edge from another triangle. And in addition, you can also put these edges in 2 orientations under cis or trans. So this means that altogether you have 12 basic types of papers. For example, Watson-Crick, Watson-Crick, where you take 2 Watson-Crick base pairs, and then it can be in cis or trans configurations. And those canonical base pairs are essentially those which are CWW, but there are many more which are also quite interesting, and they will be interesting to us. There is also some specific notation, and here we have examples how those different edges of bases can be matched together. So we are going to look for this genus analysis, but taking into account those different base pairs, also non-canonical ones. But in addition, we have to take care of one subtlety, which is that in case of RNA in particular, several chords might end in the same residue, or in other words, the same base might be in contact with several other bases. So this is example like here. We have this base denoted C12 here, and this is in contact with 2 other ones in this configuration. And such a configuration could not be translated to this chord diagram in a way which would give some definite genus. So what we do, we split this single base in such a way that chords do not intersect, which makes sure that this genus that we obtain is minimal. So having now this machinery, we, as a warm-up, what we can do, we can look at all these RNA structures and see what we get if we compute this genus for them. So this is what we are doing here. I should also mention that similar exercise was done like 10 years ago by Bon, Vernizzi, Orland, and Z. However, they looked only at canonical base pairs. We also look at non-canonical ones, and then we find some interesting manifestation of the structure of those base pairs on the level of genus. So as I mentioned, there are several hundred of those RNA chains. You can find them in PDB, or there are other servers like this RNA 3D Hub. This is example of some particular chord diagram which you get from real RNA structure, and those different colors and dashed or not dashed arcs correspond to different types of those base pairs that I mentioned. And this is the result that we find of such an analysis. So we looked at almost 500 structures, and we looked at different configurations or different types of base pairs. So first of all, we look at these canonical ones, CWW, which are drawn here. And this plot shows you how genus of the structure depends on its length. So one thing which we immediately see is that this genus grows more or less linearly with the length of the structure. You can also clearly see 3 groups of RNAs. One of them are quite short, shorter than 1,000 nucleotides. And then there are 2 groups, one which consists mostly of those smaller domains of ribosome, and then long domains of ribosome. And you can also see how this complexity depends on introducing various types of those bonds, or considering various types of base pairs. So this, again, red plot are just canonical ones, and the blue plot corresponds to taking into account all possible base pairs. So you, of course, expect that then genus would be quite large. But you might ask whether some of these base pairs are also particularly interesting. And it turns out that those which involve sugar-sugar interactions are interesting. You can see that if you make a plot, this green one is the plot where you take into account all base pairs, but apart from those of sugar-sugar type. And you see that now like a distance between these 2 plots is almost the same as between these 2 plots, which means that those sugar-sugar interactions are more or less as important from the viewpoint of this complexity as all those other types of base pairs. And this is so because sugar-sugar interactions are responsible in particular for helix packing interactions. So this helix packing introduces many of these crossings in chord diagrams when you draw them, and you say it like explicitly in this graph. So this is one manifestation of how this genus could be useful. You can also look at more detail. I will not discuss that too much here, but if you are interested, I can present that later. We have, of course, classification of these different RNA chains depending on what genus you get and which base pairs you consider, and so on. So this was just like a warm-up exercise, but as I mentioned, it was also done just for canonical base pairs some years ago by another group. But what, in fact, we do mainly in this work, we introduce some a bit more complicated function, which is called genus trace, or at least this is how we propose to call it, which encodes information not only about the genus of the whole chain, but it encodes information about various subchains. In particular, if you fix one end of the chain fixed, then you can consider various subchains which end at various places, and you can compute genus for those subchains, and then you can make such type of a plot. So this is an example how it works. This is some particular, again, in this case, RNA configuration, and here is simplified picture. You can see that if you go along these different nucleotides, you don't get any crossing until you reach the position 20. So before 20, you have at most this type of configuration. So the genus is 0, and this is what is shown in this plot. Here we have a position number. If we have some position, let's say 10, this means that we look at the subchain from 1 to 10 and look what the corresponding genus is. Before we get to 20, we get always 0, but then something interesting starts to happen, and we get higher and higher genus. We get this type of a plot. And it turns out that these plots turn out to be very interesting for various structures that you can analyze. So here is an example for the ribosome chain of this particular PDB code. And we made these plots for various types of those base pairs. So we order them in some particular ordering, the one that I mentioned before. So starting with canonical ones, and then we order them in such a way in which forming those different base pairs is less and less possible. So there are some also servers which tell you in how probable or how often various types of base pairs appears, and we chose some ordering from those servers. So again, this bottom plot corresponds to computing this genus trace just for canonical ones. So this is what you get. And then we computed for various others sets of base pairs, just considering more and more interactions. And the top plot corresponds to considering all possible interactions. So, of course, one thing that you expect is that these plots will be increasing. So this is nothing peculiar. But if you look in more detail, you find manifestation of various structural elements in these plots. So one very interesting observation is that you can see that these plots encode how this given chain is divided into various domains, which is the case of those ribosomes. And these vertical lines, they are drawn here where there are boundaries between domains, and you can see that they correlate with these flat areas in this plot. So somehow these plots give you a quantitative way to to tell how a given chain is divided into domains, which is in fact not that trivial task as far as I heard. It is not quite obvious, at least in some cases, to define rigorously different domains. So this could be one way to define them. And also what is quite interesting that you see those different spaces between different types of interactions, and they are also meaningful. So I already mentioned that these helix packing interactions should correspond most to the genus because they introduce a lot of this crossing of those chords. And this is indeed so. So this is clearly the case that the largest distance between different plots in this figure appears when we add this sugar-sugar interactions, either cis or trans. So in fact, for helix packing are responsible those trans sugar-sugar interactions, and then also A minor interactions, which also introduce this type of crossings, are more precisely CSS interactions, and they are clearly the most introducing the most distance between corresponding plots. So this is a kind of information you can deduce from analyzing of those graphs. And then you can repeat such an exercise also for proteins. In that case, you have to define bonds or those arcs in appropriate way. So the way we do that, we just consider contacts, which are based on the data from this mock server. And we can draw similar genus traces and see whether some information is encoded in them. In fact, you could also consider different types of contacts, for example, between different structural elements. But in this picture, I just considered all possible contacts. And what we see is also similar as in this RNA case, that somehow we detect division of this protein. This is some particular actin binding protein taken as an example. We can determine how this is divided into various domains. So those more steep parts of the plot correspond to various domains. They are given in various colors. And then there are some flat regions between them drawn in red. So we hope that all this could be a tool which might be used in analysis of various types of macromolecules. And well, if you, as in RNA, introduce and analyze more types of contacts, then you can deduce even more interesting information. And so this is some, let's say, data based on real structures. And in the last part of this talk, I'd like also to mention that this analysis of genus is quite interesting and also inspiring for mathematicians. And it can be analyzed from the viewpoint of so-called matrix models or random matrix theory. This is what we in particular did in this and some other papers, also with Jürgen Andersen and Chekhov, Bob Penner that I mentioned before, and Christian Reidis. So now I will focus on some simpler model where I don't distinguish between different types of interactions, but I just want to ask a simple question: how many configurations of a given genus and with a fixed number of those chords are possible? And it might seem as a very simple question comparing to real problems in RNA or proteins. However, already this question is related to very deep and complicated combinatorics, which I'd like to briefly present. So, of course, you could start drawing those configurations one by one and counting how many of these configurations there are. If you have just one backbone and one chord, then there is one configuration. So this one corresponds to the coefficient of z in this function. I just want to write here a generating function for those configurations. If you have two chords and you want to have genus 0, which means that they should not intersect, then you have two possible configurations. So this is this number 2 here. Then if you have 3 chords, you can draw 5 non-equivalent configurations. So this is 5 here, and so on. And you can realize that the series is the expansion of the following function. And those numbers 1, 1, 2, 5, 14, and so on, these are very well-known Catalan numbers. They are very well-known in combinatorics. But this is just the simplest situation when you have genus 0 and 1 backbone. And you might ask whether it is possible to find similar generating functions for arbitrary genus and arbitrary number of backbones, and then write similar series with coefficients which will tell you how many non-equivalent configuration you have. It turns out it is possible, and to do that, you can use the machinery of random matrix theory, in which these chord diagrams, which we used before just to find the genus, these chord diagrams appear as very particular type of Feynman diagrams. So this is what we did in that work, and we found that the answer to this question, namely what are these numbers C, G, B, is encoded in the following integral, which mathematically is quite complicated. So even though I am considering quite simple model of those interactions from mathematical viewpoint is quite complicated, I make an integral over matrices. This dm denotes that I have to integrate over matrices of arbitrary size n by m, and moreover this n has to go to infinity if I want to get answer for all possible values of genus. And then I make integral of the exponent of the trace of some function which can be shown, well, I will not do that here, but it has to take the following form. So if you would have just x squared, this would be just a Gaussian function, but we somehow corrected by additional term, which is proportional to 2 parameters, s and t. And somehow these parameters encode the information about the number of backbones and the number of those chords that we have in the result. So then the statement is that if you are able to compute such an integral and expand it in the limit where this n goes to infinity, here is another parameter which you can think of as Planck constant if you make some analogy to quantum mechanics. Then you make the limit where n goes to infinity, but this product is kept constant, which means that h bar has to be small. So it turns out that this has expansion, which looks like exponent, and then some series in this parameter h bar, which is small, and coefficients are certain functions, which I called fg. This g corresponds to this genus I am interested in. And then they encode this function cgb with the argument which is t squared, so this is why I had to use t here, and also the coefficient which somehow counts the number of backbones is s here. And it turns out that there is quite complicated machinery in this random matrix model referred to as topological recursion, which enables us to compute all this fg. When we compute them, we can then expand them and find this generating function cgb. So this is the result for f2, which already seems quite complicated. What is somehow important is that this complicated result encodes all functions for all these functions c with genus 2, but arbitrary number of backbones and arbitrary number of chords. And then you can expand this result in powers of s and t. And for example, you find the following generating functions for the number of those configurations with genus 2 and for backbones and arbitrary number of chords. Then you can play with that, and you may use the knowledge of how many of these configurations are. For example, you can compare that to real structures which you might find in PDB regarding RNA. So even though this model might seem simple from biophysics viewpoint, it's quite involved mathematically. It somehow shows that things which are simple in mathematics may be complicated in biology or the other way around. So to summarize, I was trying to convince you that this genus, and in particular this new function genus traits, may provide a measure of complexity for macromolecules. And in particular, it detects boundaries between domains if you analyze real structures. And also it may detect different types of interactions and somehow quantify how much they contribute to complexity. And on the other hand, I tried to show that even if you make very simple model of RNA interactions, it has very deep relations to combinatorics, Feynman diagrams in matrix models. And also, I didn't stress that, but also these chord diagrams have interpretation as, well, in the language of moduli spaces of Riemann surfaces. This is also the reason why those mathematicians are interested in these topics. So I think that's what I was going to present.
Are there any questions?